Determine the open intervals on which the function is increasing, decreasing, or constant. We have the function f of x equals x squared minus 8x. Its graph is over here to the right. Any location on your graph where it is positively sloped is an area or an interval of increasing. The vertex is located at 4, -16. To the right of the vertex, the graph is positively sloped or increasing. These open intervals, they're just keeping track of what values of x satisfy each description. So this graph is increasing after 4, and decreasing is anywhere it's negatively sloped. That's anywhere less than 4. In this second example, we have f of x equals x cubed minus 6x squared plus 5. Its graph is over here to the right. There is a middle section between the values of 0 and 4 where the graph is negatively sloped. So the open interval of decreasing is from 0 to 4. There are two separate areas where the graph is positively sloped. All values of x less than 0, that's the first interval, or all values of x greater than 4, that's the second interval. You just join those with a union. We have a piecewise function on this slide. The function is defined as the line 3x plus 2 as long as your values of x are less than or equal to -2. So that's this piece of the graph. Once your values of x are greater than -2, then your graph becomes the parabola x squared minus 8, and that's this part. There's a small section where the graph is negatively sloped, and that is between the x value of -2 and 0. -2 to 0, the graph is decreasing. The graph is increasing in two separate intervals. The first interval is any value of x less than -2, that's this interval, or any value of x greater than 0, and that's this interval. Both of those sections are increasing. Determine the interval or intervals on which the function is greater than or equal to 0. A function is positive anywhere above the x-axis. A function is negative anywhere below the x-axis. It's exactly 0 on the x-axis. So basically, we're looking for the values of x for which the function is on or above the x-axis. We have two x-intercepts for this parabola. They occur at 0 and 2. Any value of x less than or equal to 0 results in a positive function value. Any value of x 2 or larger results in a positive function value. So we use brackets at the x-intercepts to signify that we keep those values in our interval. The left part of the graph that's above or on the x-axis is any value of x less than or equal to 0. The other part is any value of x greater than or equal to 2. Determine the interval for which the function is greater than or equal to 0. This time we switch to square root of x minus 2 as our function. Its graph is over here to your right. Again, greater than or equal to 0, we're interested in values of x on or above the x-axis. Any value of x for which the graph is on or above the x-axis. The x-intercept is at 2. Any value of x larger than 2 is on the graph above the x-axis, resulting in a positive function. So long story short, the interval from 2 to infinity, including 2, results in a function value that's either 0 or positive. Let's switch to an absolute value function, determine the intervals for which the function is greater than or equal to 0. We have the function absolute value of x plus 1. Its graph is over here to your right. It has a vertex at -1. This graph is on or above the x-axis all the time. So its interval is -infinity to +infinity. You actually include the -1 because you can be equal to 0. And finally, we will look at an example to find the average rate of a change of a function over a specified interval of x values. Okay, so we have the function x squared minus 2x minus 8, and we're asked to investigate its average rate of change from x being -1 to x equals 5. Now, you don't have to graph these to find the average rate of change. I just included this in class to give you a visual. This particular function is a parabola. At -1, the function is equal to -5. That means the point -1, -5 falls on the graph of the parabola. At the other end of the interval at +5, your function value when x is 5 is 7. So you pair those up, 5, 7 is another point on the graph. If you draw a line through your function that goes through these 2 points, -1, -5, and 5, 7, average rate of change for the function is the slope of that secant line. The way to calculate this without doing the graph is you calculate your function value at the right interval endpoint, so that's f of 5, minus the function value at the beginning value of x of the interval, f of -1, and then you divide that by the length of the interval, 5 minus -1. Our function value at 5 is 7. Our function value at -1 was -5. 7 minus -5 is 12. The length of this interval from -1 to 5 is a total length of 6. 5 minus -1 is 6. 12 divided by 6 is 2. So in this particular interval, this function has an average rate of change of 2 units. I hope the visual helps out. You don't have to you don't have to graph the function and draw a secant line if you don't want to. I learn better by visuals.